Good afternoon. The next speaker is Dr. Praful Mankar, and I am indeed honored and privileged to welcome a good friend of mine. Dr. Praful is currently a faculty member at IIT Hyderabad, sorry, IIIT Hyderabad, and earlier he was a postdoctoral research scholar at the Bradley Department of Electrical and Computer Engineering at Virginia Tech, USA, from 2017 to 19, where he worked with none other than Dr. Harpreet Dhillon, who is considered to be an expert in the area of modeling and analysis, and especially stochastic geometry. So he has experience working with that particular team, which is a leading team in this area across the whole world. He has received his master's and PhD degrees in telecommunications system engineering from IIT Kharagpur, and the bachelor's degree from Amravati University in electrical and communication engineering. During his stint at IIT Kharagpur is where I met him, and we became good friends, which continues to this day. His research interests include the modeling, analysis, and design of modern wireless communication networks. And today he shall discuss the application of stochastic geometry for cellular capacity analysis or cellular network analysis in general, and also explain to you the relevance of stochastic geometry and similar tools in the context of 5G. So with that, I welcome Dr. Praful once again, and now I request him to start his presentation.
Hello. Can you hear me, Shahan, sir?
Yes. Only thing is, you need to be closer to your microphone and speak a bit louder, sir.
Okay. Am I audible now?
I think you need to just raise the volume a bit, sir. That's all, and you would be sharing your screen, I believe.
Yeah. Let me share my screen first.
Yes.
So, can you see my screen now?
Yes.
Okay. Thank you. Thanks for inviting me for this presentation, and I welcome all the participants to this online program on towards 5G and 5G communication and beyond IoT and machine learning. And I'd like to also thank the AICTC for giving me this platform for sharing my research interest. So let me turn off my video now for the better utilization of bandwidth. So, okay. So mostly my research is concerned on the application of stochastic geometry for wireless networks, in particularly next modern cellular network. So outline of my presentation is first I'm gonna give some introduction why this stochastic geometry is needed for modeling these modern cellular networks, especially 5G and beyond. And then I'll go to little bit background to develop your background on the stochastic geometry. In particularly, I'll talk about the Poisson point process, which is most widely used point process for modeling the cellular networks. And then I'll apply this stochastic geometry for the analysis of the cellular network. Therein, in particular, I'll focus on three types of network. One is ad hoc network, another is cellular network, and within cellular network, two types of communication. One is uplink and downlink, which I'll deal in separate. So you can already see from this diagram that the cellular network, 5G cellular networks are becoming very complex. The topology is growing to be a random, and vast in terms of dense deployment of the base stations. Traditionally, actually, the cellular network were having the base station which were covering larger coverage and providing ubiquitous connectivity. But recently, this cellular operator started coming up with a more advanced base station like FEMTO and BICO, which are actually deployed into the coverage dead zones and hence trying to increase the network capacity. But with the inclusion of this kind of networks, it's growing. The topology of the network is going to be a complex and random. Uh, on top of it, actually, this cellular network are also increasing their density to meet the more demand on the mobile service demands. Their objective is no more on these providing the ubiquitous connectivity. And on top of this, all these base stations are communicating in the same spectrum, and to increase the spectral efficiency, they are coming up with the advanced way of communication, wherein all these transmitters and receiver are communicating over the single frequency, and because of which actually the universal reuse of the frequency. There is a huge intercell, intertire, and intertire interference actually, which is coming, and which is a kind of performance limiting factor for this kind of wireless networks. So, and since this both signal as well as the interference are the location dependent quantities, therefore it is very much required to cover the spatial randomness into these locations of these different kind of base stations. So now let's look at what are the available models that are being used for modeling the location of cellular network. So this represents one kind of grid-based model, which was kind of heavily used during the initial phase of the development of the cellular network. It was successful because during this initial period, the focus was on the providing ubiquitous connectivity. So because of that, with that objective, the cellular operator were deploying these base stations with little bit strategies, and which was kind of closely resembling with this hexagonal structure. But this structure actually heavily relies on the simulation. They limits in they do not provide that much mathematical attractivity in the performance analysis. And this, but nowadays, since the cellular networks are growing as a complex in terms of locations, to meet the demands, mobile demand, which are actually random in the spatial pattern. So with that objective, with that thing in mind, recently people have started switching towards this spatial random model, wherein the locations of base stations, which are denoted by this red dot, are actually drawn from some random point processes, and then started applying this for the actual cellular network and do the performance mathematical analysis. And so theory of this as the theory of this point processes are very rich, and they have very rich mathematical properties which we can directly borrow here and perform the mathematical analysis of the cellular networks. And means we can realize this multiple independent point processes, and then we can extend this multiple point processes to the analysis of the multi-tier networks. And let's look and this third diagram represents the actual deployment of the 4G networks. So which we can already see that this spatial random model is closely resembling kind of the actual topology of the 4G deployed network. So there is actually this need for focusing our attentions towards these point processes. So with that background, actually, I'll like to give a little bit tutorial on the stochastic geometry. So mostly we'll focus on the Poisson point process, which is one of the simplest and more used point process for the performance analysis of wireless networks. So the definition of this Poisson point process goes like this. So first of all, this point process is nothing but is the collection of points, randomly deployed points in a plane. So which are actually following some probability law. And then now coming to the definition of Poisson point process, the number of points in a set is Poisson distributed. For example, we represent this point process using phi, and and then phi of A represents the number of points in set A. So this is actually the Poisson point process. The first condition for this is this phi of A is a Poisson distributed random variable. And the second condition is that the number of points into disjoint sets are independent. That means the number of points in set A and in set B are independent. So let's take a look at the few examples of this Poisson point process with different intensity functions. So if we make the intensity function as some kind of Gaussian function, then resulting point process is going to look like this. Clearly it's not homogeneous over the plane, as this towards the origin we have more densely deployed points as compared to towards the edge. So this kind of density functions are useful for modeling the users in the hotspot locations. On the other hand, homogeneous Poisson point process, where intensity is just constant across the plane. So here you can see that these points are uniformly distributed across whole plane. And this kind of model is useful for modeling this large-scale cellular network, which is actually close to, which is the requirement for the cellular network. Now let's look at the few properties of the Poisson point process. In particular, we'll focus on the homogeneous case of the Poisson point process for modeling the cellular network base station basically. So the mean measure of the intensity function is the expected number of point is nothing but the intensity measure of that set A, and if we are setting that intensity function lambda x equals to just lambda, then the resulting expected number of points in the set A will be lambda times area of that set, and by that definition, the density of this Poisson point process, that is equal to the expected number of points in a set divided by area of the set, is reduces to lambda, and which is just independent of the area any set. And it is interesting to note that this expected number of points in a set is equal to the expected number of points in a translated version of the set. That means this phi homogeneous Poisson point process is kind of translation invariant, and which makes it as a stationary Poisson point process. So one of the most useful property for our analysis is kind of wide probability of this. So which is nothing but the number of points in a which is nothing but the probability that a given set is empty. And since the number of points in a given set is Poisson distributed, and that number has to be 0, so which will reduce to this exponential of lambda times area of that set. And it is please note that any two points having equal wide probabilities, that means they are in the same distribution. So with that in mind, we can actually look at now the superimposition of 2-point processor, two independent Poisson point processors. Let's say we have phi1 and phi2 as independent point processes with densities lambda1 and lambda2. And if we make the superpositioning of them, then resulting point process is also kind of Poisson point process with intensity lambda1 plus lambda2, which can be directly actually inferred from this wide probability of this superimposed point process. So means that wide probability will be equal to just joint probability of phi1 and phi2 to be independent, to be empty. joint wide probabilities of this phi1 and phi2, and which will reduce something like to this expression. And from this expression, we can see that this is the wide probability of this Poisson point process when the density is λ1 plus λ2. Now, another property, useful property, is the independent thinning. So let's say we have a point process phi, and we are retaining its points in another point process phi t with probability p. Then the resulting point process phi t will be also a Poisson point process, as is expected. Uh, as is the wide probability can be derived something like this, and which is nothing but the wide probability of the Poisson point process with density p times lambda. And this kind of this independent thinning is very useful. Let's assume that the location of the transmitters are following some Poisson point process, which is phi basically, and they are transmitting as per the aloha transmission strategy. That means they are transmitting with probability p. Then the number of points transmitting at any given time instance will be also forming this Poisson point process with density p times lambda. So this palm distribution is very useful for spatial averaging of some properties of the points. Actually, it is nothing but is a conditional distribution of a point process, given that there is a point present at the origin. So, for example, look at this case. So let's say we have let me. Let me use pointer. So let's say the point x has some property qx, and we want to see that what's the expected properties of this qx are following some event y. So what we'll do actually normally, we'll take the sum of this individual probabilities of qx following event y, and divide it with the number of points in the larger set. So by the palm distribution, what we can do actually, we can just put a one point at the origin and just see its location, whether its properties following the event y or not. So we don't need to do the spatial averaging over individual point in the set. We can simply do it for the fixed located point at the origin. And then reduced palm distribution is kind of the conditional distribution of the point process on the condition that there is a point at the origin, but it's not being counted in the expectation. And this, for example, means for example, let's look at the number of points in a ball of center at the origin of radius r. If we want to see that the wide probability of this ball, then in the reduced under the reduced palm distribution. Basically, this is kind of useful for measuring the interference at the typical locations. Typical location of the typical link, which receiver is fixed at the origin, let's say. And by the use of Silvernaik's theorem, we can exactly say that this reduced palm measure is equivalent in the distribution as the original distribution for the case of Poisson point process. That means this wide probability under the reduced palm distribution is exactly equal to the wide probability of the Poisson point process, and which is nothing but the pi r square. Which is nothing but the exponential times of lambda times area of that circle. Okay, so now with that background on the stochastic palm distribution, we can actually develop now some useful properties of the Poisson point process, which is the nearest point distribution. Nearest neighbor is nothing but the distribution, but the distance between two neighboring points in the Poisson point process. So the distribution of the nearest neighbor distance distribution is nothing but the CCDF of the distances from the nearest point from x from x to the nearest point in the phi on the condition that x is included in the phi. And since we are forcefully including x into the phi, we have to look this this CCDF function, which is g of r, under the reduced palm measure. So for getting the nearest point to the x, we have to look into this probability that a ball center at x is empty. And without counting the point x, that's what the reduced palm measure. And since it is equal, this reduced palm distribution is equal to the original distribution, we can actually directly derive this g of r to be a wide probability of the Poisson point process. Then coming to next useful property is contact distribution. So contact distribution is nothing but the point, the nearest point, distribution of the nearest point from the origin, and which means the probability of the nearest point from the origin. We can get that directly using the wide probability, something like this. And it is useful actually in the context of wireless network, because if we had deployed the base stations at the as the Poisson point process, and then users as an independent Poisson point process, then the distance between mobile user and then is serving base station, which is the nearest base station to the location of user, can be directly served using this contact distribution. Now, there are a few functions like k functions, jump functions, which are very useful for you to see if the real life data is matching with the Poisson point process or not. And if they are matching, if there is some clustering between the points, or if there is a repulsion between points, then this to see that kind of actually properties of the real life data, then you can actually use these two functions, basically k and j functions. So basically j function is nothing but the distribution, is the ratio of this distribution of the nearest neighbor distribution to the contact distribution. And since for PPP you can see that f of r is just wide probability, and g of r is also kind of wide probability. You can directly see that this j of r is kind of 1 for the Poisson point process. And you can see that this is non-parametric test, basically. So in order to test the real life data, you don't need any parameter of that data. You just need those locations and feed them into the g of r and the f of r form, and then evaluate this j function. And if that j function is turned out to be 1, then you can see that your real life data is distributed as the Poisson point process. Then another useful function is the k function, which is nothing but the mean expected number of points in a ball of radius r. And of course, means since the number of points distributed under Poisson point process, the number of points distributed in the set is equal to lambda times area of that set. So k of r will reduce to the lambda times pi r square. And then this pair correlation function, which is just the derivative of this k function divided by this identity. And from its definition, from this k of r substituting directly here, you can get actually g of r equals to 1. And the g of r is very useful actually to gain some perspective on the real life data. For example, if there is clustering between points, then this g of r function will be kind of will be greater than 1. If there is a repulsion between the points, then this g of r function will be less than 1. Now let's say if you have some function of these points, x i's, which are distributed over the plane, and if you want to take that sum of that function over the whole point process, then the Campbell theorem says that just integrate that function over a whole plane and scale it with the density of the point process. So you can actually without doing this rigorous sum for each and every point over the whole plane. You can get this your sum by simple one integration. So that means you don't need to realize these locations at all, as long as you know that this phi follows this Poisson point process with density lambda. This, another property is kind of second order statistics of this process. So let's say we have a function which is a function joint function of two, which is bivariate function basically. Then its expectation over phi can be already something like this. Let's look at the utility of this these two mathematical statements. Let's say we have points distributed as a Poisson point process, which are indicated by these blue dots, and which are basically transmitter. And we are now you want to receive, and you are receiving the interference from all these transmitter at the origin or at this location y, and which is given something like this, where this L of xy is a path loss, and which is just depend on the location distance between x and y. So this represents the cumulative or aggregate interference received at the location y. So by since it is sum over phi, we can directly apply this this Campbell theorem to calculate the mean interference. So mean of this aggregate interference will be just integration of this path loss function over the whole plane and scaled by the intensity function, and which will something reduce like to very simple thing, something like this. And the second order, let's say if you want to derive the second moment of the interference, then then you can derive something like this. By binomial expansion of this function, you can write you can split it into two terms, and here you can apply this Campbell's theorem, and here you can apply this second order statistics of the Poisson point process, and then directly arrive at this expression, which is quite remarkable. And then this and then mean the variance from this mean first two movements, you can directly come to the variance of the interference at location y, something like this. Now coming to the function of different nature, means let's say you have function f which and you want to take the expectation of product of that f function. Then by means of this probability generating functional, you can actually derive something something like this. And then now let's look at the relation between sum and product function of this nature. Let's say f of x, s of x is kind of some function. Then the expectation of this form of this sum function can be written something in this form. You can directly bring out this summation in s as a outside of this exponential as a product term, and then look at this g of f. G of f is the expectation of product of this function f. So here it will be a g of f, g of exponential of tf, and which is nothing but the probability generating function. So with this relation, and note that this is nothing but it's a Laplace transform of this function, some function, right? So and since some function is kind of it represents our aggregate interference, we can say that this is the Laplace transform of the interference, and which can be directly evaluated using this probability generating function. Let's look at this. So Laplace transform of interference received at location y can be written something like this, and by PG by the relation between this sum and product of functions, we can directly evaluate or derive this Laplace transform of the interference at received at the location y, something like this. And if you simplify, means if you convert this Cartesian coordinate system to the polar coordinate system, then you can directly arrive at this expression. Since this phi is kind of isotropic, so means it is invariant to the direction. So because of that, actually 2 pi you can directly bring out, and then integrate remaining function as a function of just distance or the radial distance. And let's look at now. Let's try to derive the mean interference using this Laplace transform. So which is nothing but the negative differentiation of the Laplace transform at t equals to 0, which will directly give you this, and which is nothing but the our mean interference that we have derived using the Campbell's theorem. Now, with this brief background on the on the stochastic geometry, let's look into the its application for the ad hoc network first. So in ad hoc networks, actually we model the transmitter receiver pairs using bipolar Poisson point process, and bipolar Poisson point process goes something like this. So we distribute the transmitters using Poisson point process with density lambda, and allocate one receiver to each transmitter, which is placed at distance r in a random direction. So this will represent actually our transmission receiver pairs. And let's say we are having aloha protocol. That means each transmitter transmit in a given time instance with probability p, independently of what other receivers are doing, and independently of what this receiver will do in the future. So since this point process is homogeneous in time as well as the space, we can actually say that we can apply here independent thinning, and then say that at any given time instance the active transmitters are kind of forming a Poisson point process with intensity q times lambda, where q is the transmission probability. So now, and for this system model, we will consider power law path loss model. So where the path loss from will be just distance raised to power minus alpha, where alpha is the path loss exponent, and we'll assume the Rayleigh small scale fading. So basically HYX represent the Rayleigh fading gain between transmitter X and receiver Y, and which means by definition of Rayleigh, this HYX will be kind of exponential distributed. So now for the performance analysis, we'll using the Silvernaik's theorem that we have earlier seen, we'll fix the transmitter, a typical transmitter at x0, and fix its corresponding receiver, which is at distance r, and place it at the origin. Thus the SNR received at this typical receiver will be something like this. So so this is the signal received on this on this typical link divided by interference received at the origin, and which is something like this, which is given something like this, where zeta x represents the activity factor, means zeta x is 1 if the transmitter x is active, otherwise zeta x is 0, and then the zeta x being 1, the probability of zeta x being 1 is equal to q, which is the aloha parameter. And note that so you can see that we have conditioned one typical transmitter at x. So we'll have to deal with the reduced palm distribution, and which is nothing but equals to the original distribution by the use of this Silvernaik's theorem. So the addition of this extra transmitter will not affect the interference which is received from the all other points at this location. So our performance metrics are actually something like this. So what we are interested in knowing is that what is the success probability. That means what is the probability that the typical receiver will experience the SINR above threshold. And then this probability can be actually interpreted as this. Basically, we are carrying out this this distribution under the reduced probability, but because of this spatial, its relation with the spatial averaging, actually we can relate it to something like this. So it represents the probability that the randomly selected receivers achieve, means let's say you have a point process phi, and you select one point randomly, one transmitter or receiver randomly from your whole set of transreceiver pairs, and it represents that particular receiver receives the SNR threshold above beta, or it can be also interpreted as average fraction of the total number of receivers experiencing the SNR threshold greater than beta. As you can directly see, that is a very useful probability, but for knowing that what's the average coverage of your whole network. But you can see that it is already average over the whole space and time. But in actual network setup, different receiver experience different successful transmission probabilities because of their signal qualities are location specific. So for that purpose, actually, we can define something like this conditional success probability, which is nothing but the probability that the SIR received at the typical receiver place at the origin is above threshold, condition on all the locations, that is phi. And then take the distribution of this conditional successful probability, which is generally called as a meta distribution, and then is a very important metric actually. It provides some fine-grained information on your network, something like. So by setting x, let's say, means if you set x equals to 8.8 and then threshold equals to let's say 7, then you can actually precisely from this metric you can gain the information like that average was the fraction of the number of users achieving 80% of the linked reliability when the SNR threshold is 5 dB or 7 dB, whatever which we choose beta for. So now we'll present this meta distribution analysis first. So as we have already defined that meta distribution is nothing but the distribution of the conditional successful probability. But in this stochastic geometry setup, it's very hard to get this actual distribution of the meta conditional successful probability. So for that purpose, actually, we'll set our objectives to deriving the moments of the conditional successful probability. So for that purpose, let's see for conditional how the conditional successful probability looks like. So it's just a probability that the SINR is greater than beta, given phi. That means is being averaged over all the fading gains. That means is that it can be also treated as a temporal successful probability condition on the spatial location of the all transmitter receiver pairs. And by using a few mathematical tricks, we can actually get it something like this, and which is still a function of phi, as you can see that. And now coming to the moments of this meta distribution, we need to derive it under the reduced palm distribution, because remember we have a typical corresponding transmitter placed at x0, which is corresponding to our typical receiver, which is placed at the origin. And then it's a moment, and then the peak moment of this conditional successful probability is something like this whole expression, which is the conditional successful probability raised to power b, and then take its expectation with respect to this reduced palm probability. And by PGF, and remember this reduced palm expectation is equal to the original palm expectation for the case of Poisson point process when by this Slimnik's theorem. And now recall that we have looked at this PGF or probability generating function of the Poisson point process, which was actually expectation of the product of some function. So which was something was having this form. So here you can relate actually our MB has also similar form of this expression. So let's substitute this expression, replace this expression with the F in the here, and then we'll will get the bit movement of this meta distribution, which is something like, which is straightforward, is something like this. And by further simplification, we can get a closed form expression for this bit movement of the conditional successful probability, and which is kind of very intuitive to interpret. Means if you are increasing q, that means which is the transmission probability of the interfering devices or transmitter, this movement of these coverage probabilities are going down. Or if you increase the distance between transmitter ratio pairs, these movements will again go down. Or if you increase this beta, that is the SNR expectation, again this movement will go down, which is kind of intuitive, right? So the special cases of this movement cases. So remember we have defined successful probability before introducing the meta distribution. So which was nothing but which is the spatial temporal average probability of the SNR being above certain threshold. And you can see that so this metric we have defined as a conditional successful probability. So if we take just the expectation of this setup, this probability, it will be nothing but the successful probability, and which is equal to the first movement of this conditional successful probability. That means the first movement of the conditional successful transmission probability, which is average over the space time. Look at now another special case of this is the local mean delay. Using this MB, we can also arrive at the local mean delay. Let's say this transmitter is transmitting continuously to this receiver until it makes its transmission successful. So let's say in first transmission, the link is failure. Another transmission, the link again fails, and in third transmission, so links get the packet gets successful transmitted. So one would ask, what's the expected so what's the mean number of slots this transmitter requires to successfully deliver this packet? So which is nothing but the successful transmission rate, which is just 1 over the conditional successful probability, which is conditioned on all the points of interfering transmitters. And now if you want to know what's this, now this delay is kind of conditional phi. Now if you want to know the average delay of all transmitters in the whole network, then we have to just take the expectation with respect to phi under this reduced pump probability, and which is just the expectation 1 over ps of beta, and which is nothing but the first negative movement of the conditional success probability. So that means this kind of we have seen two actually useful cases of this metric meta distribution, which was actually something like this MB. Now coming to the result and discussion section of this segment. First, let's look at this successful transmission probability, which is the first movement of this meta distribution. So you can see that as this Q, what is the transmission probability of aloha, which is the aloha parameter, as it increases, the successful transmission probability for given beta start to drop, which is quite intuitive, because with increasing Q, we are increasing the interference, and thus the successful transmission probability for meeting this particular value of beta will drop. Another is delay, so which is again in similar lines with this, which is again plotted against this various values of this aloha parameter Q. As we increase this Q, the interference starts to increase, and thus the successful transmission conditional successful transmission probability will start to drop, and the inverse of that probability is kind of your mean delay. So the mean delay actually will shoot at the initial values of beta as you increase the Q. Now that we have already these movements of the meta distribution, so what we do actually, we use the first two movements of this meta distribution and match with the with the beta distribution for getting the approximate distribution of the meta distribution. So here you can see that these solid lines represent the simulation result, and these circular lines represent this approximate result of the beta approximation basically. So from this result, you can see that if you set your yes and no threshold was set something 3 dB in this case. So for 3 dB of yes and no, and 80% of the link reliability, if you set, then with Q equals to 1, you can achieve almost 30% of the user will get the will meet the link reliability of 80%. With Q equals to 0.5, almost 50% of the user will meet the link reliability of 80%, and with Q equals to 0.1, almost 97, 98% of the user will achieve the link reliability of 80%. So that means it's this meta from this graph is clearly visible that how useful this meta distribution metric is. Now coming to the downlink analysis of the cellular network. So what we do actually, we draw the locations of base station. We assume that the location of base stations are following the Poisson point process, and we assume that the base station users are associated, which is based on this maximum mean signal strength received policy. That means the base station which is providing the maximum signal gain, that base station is becoming a serving base station. So under that association policies, our network will look something like this. And as you can see that this kind of model actually is very nicely represent this actual network setup, and it has actually the advantage of this kind of model is that it follows this. Follows the network topology accurately, and another is the analytical tractability. But the only disadvantage of this is that the base stations can get arbitrarily closer to each other. For instance, you can see this sample points here or this sample points here, which are actually very close to each other. And in real life network, two cellular base stations cannot be as close as this much. Okay, now coming to system model. So we'll actually assume that the base station point user locations are independent of the base station point process, and we'll perform the analysis for the typical user. And because of the stationarity of this Poisson point process, we'll place the typical user at the origin. Okay. So for this user, the serving base station becomes its nearest base station. That means the cell which is covering the origin, and that base station is represented by B0, and all other base stations other than this X, other than this B0 will be interfering point, base stations. And we also assume that all the base stations are always active. That means our network is kind of saturated. That means all the base stations has traffic to transmit to their mobile users. Again, we will assume the power law path loss model, something like this. So that means the path loss from this base station to here will be just Rx raised to power minus alpha. Again, we will assume this Rayleigh fading. And for this system model, this downlink SNR received at this typical user, which is placed at the origin, can be written something like this. By the way, we are assuming that all the base stations are transmitting at the fixed power. So conditional probability for the Rayleigh fading for when this hx and hpo are independently exponentially distributed, we can arrive at this conditional success probability straightforwardly to this, which is still a function of interference point process and then link between the serving link distance. So further taking expectation over hx, will arrive at this expression, which is nothing but the Laplace transform of the exponential random variable. If we apply to the here, apply that here, then you can actually get it something like this. So now coming to the peak movement of this conditional successful probability, it's just raising this conditional success probability, taking its expectation raised to power b, and then expectation is to perform over the locations and then location of the interfering base stations, which is denoted by phi tilde, and the service link distance, which is basically a product of this byproduct of this serving base station location. So in order to perform this joint expectation, we need the joint distribution of these two quantities, which is R0, which is the link distance. Remember, R0 is represent actually link distance of this typical mobile user placed at the origin. And that R0, the diagram was already here. So this distribution of R0, remember we have talked about this contact distribution. Contact distribution is nothing but the distribution of the closest point in the point process. So by that actually contact distribution, we can directly come at the distribution of the service link distance, which is something like this. And now for the distribution of this phi interfering point process, you can see that it is still from the Poisson point process, and which is homogeneous actually, just outside of this ball, because since there is no point allowed to exist within this interfering point allowed to exist within this ball, we know from that fact actually, we know all the points, interfering points are forming this homogeneous PPP outside of the ball. So that implies that all this probability, that the sum or that probability is of Campbell theorem, second order statistic, PGFL, all those probability can be again useful here for analyzing the interference condition on R0. So taking the first movement, the big movement of the expectation probability using the PGFL will go something like this. Remember, we are now performing this inner expectation with respect to interference point process. And since that interference point process was kind of homogeneous Poisson point process outside of this ball, we have to take the expectation over whole plane except this ball. And then after that, we take expectation over R, where R being a parameter of this ball, and then being a parameter of the received signal strength. So this can be again a simplified straightforward with something like this, and then this integral by just a Cartesian to the polar coordinate conversion, and then then this integral can be solved something like this, which is independent of R. You can see here. And now taking expectation over R with R being independent in the exponential term, and R being Rayleigh distributed. So R distribution is already given here, which is kind of a CDF of the Rayleigh distribution. So taking this expectation will arrive at a closed form, again a closed form for this downlink meta distribution in the cellular network setup, and which is something like this. And note that it is very interesting to note here is that this movement of the meta distribution is kind of independent of the density of Poisson of the base station location. If when they are actually working in the interference limited regime. Remember, here we have not actually considered the noise. We are we are working in the interference limited regime. So intuitively, we can see that increasing or decreasing the density of base station will not impact this spatial disparity in the conditional successful probability, because the interference, as if you increase the density of the base station, the signal the interference is increasing, but at the same time the serving link distance is also getting decreased, and which is increasing the basically signal received strength also. Okay, and then let's look at the special cases of these two cases. As we have already discussed, the successful transmission probability is nothing but the first movement of the conditional meta distribution, and which has this form basically. And for alpha equals to 4, we have an even simpler expression, which is just a function of beta. Beta is the SNR threshold, and using this success probability, we can actually get the ergodic rate of the cell or the cellular network, which is just the integration of the transmission rate over this distribution of the successful transmission probability. And for various of values of alpha, actually means increasing alpha, you can see that the rate, which is the evaluation of this integration for the unit hertz per second, means rate in nats per second per hertz, which is actually can be also interpreted as spectral efficiency, is kind of increasing with increasing path loss exponent. That makes sense actually. By increasing the path loss exponent, the base station which are actually far away from the receiving mobile device will not interfere much, as these as the path loss will start decay at faster rate for the higher values of alpha. So for cellular network, you can see that this conditional successful probabilities for all of these receiving devices, which are indicated by the blue circles, are kind of different for different devices. And meta distribution is just the distribution of all these values basically. And then from this plot, we can see that the mean of all these values is kind of this are represented by this solid curves, which is the successful probabilities plotted on the left y-axis, and then variance of these values is plotted on the right y-axis, and which is something going like this. Also, which has a peak basically at a particular beta. However, this successful transmission probability decays with the increasing SNR threshold, which is kind of intuitive. Means if you set your SNR to be very high, then it's very hard for the receiver to meet that kind of SNR level. And then again, we present we match this by moment matching. We derive this approximate beta distribution of the meta distribution and validate it here. So here basically means the circular marks represent the simulation curves, and then the solid lines represent this analytical curves. Here you can see that this approximate beta distribution kind of follows this meta distribution very closely. And by the way, now that we have exact movement of the meta distribution, we can apply the Kiel-Pilas integral or inversion to get the exact distribution. But it's kind of mathematically or computationally very heavy to do. So for that purpose, actually, we can rely on the beta approximation. And here actually you can see that for increasing the beta SNR threshold, which is beta, your probability of this meta distribution is dropping actually. For example, if your meta if beta for beta equals to 7 dB, you have only 1 minus this, so it will be almost 65% of the user will experience a link reliability of 80%. On the other hand, if you have on the other hand, if your beta equals to 3 dB, then your number of users will be achieving 80% of the link reliability will be something, it will be kind of 50%. Yeah. So now coming to the uplink analysis of the cellular network. So in uplink analysis, again, we model the location of base station using Poisson point process, and then we do the analysis for the typical carrier. So we have actually n number of subcarriers, and out of them we will randomly pick one, and we'll assume that the load or the number of, or the users are distributed equally across all the subcarriers. So the probability that one user, for that setup actually, each cell will have n number of users, and from this example, let's say we have two subcarriers or two channels. Then each cell will at any time any cell will have exactly two number of users, because we are not considering intra-cell interference. So now you can do the analysis for the one randomly selected channel or subcarrier, and then and in order to get the user distribution of that, you can thin the whole user point process with probability 1 over n, where n being the number of subcarriers. So in this setup actually, the interfering user actually can lie closer to the base station than the serving user. So for example, here, sorry, here there is no actually particular example that I can highlight here, but this is the case because of the irregular structure of this structure of the cellular network. And so in order to mitigate the interference in the uplink analysis, transmission power control is kind of essential. It's kind of essential tool for this design of the uplink network. So we'll consider that also. So transmission power of a mobile device will be directionally proportional to the will be actually depend on the service link distance. By setting this power this kind of power law fractional power control mechanism, we can see that you can mitigate some amount of the path loss, as the path loss is equal to R0 raised to power minus alpha. So again, for the analysis purpose, we'll fix the location of the typical user at the origin. So that means so we'll have a typical base station at origin where we'll be measuring our SINR, and we'll distribute the user which is representing being active into the given subcarrier, and we'll distribute uniformly at random. In each cell, we'll distribute exactly one user. And by this topology, actually, the location between base station and user gets coupled basically. So that means the distribution of the user point process is no more independent of the base station point process. And since it's coupled with the coupled through this tensillation, these points are not forming the Poisson point process. For example, in this set, the number of points in this set is not independent to the number of points in this set, because in whole this region actually there can be only one user. So with this user, so we will have this psi as a user point process, and which will actually contain exactly one point in each cell, something like this, and that is uniformly distributed within each cell. Okay, and then we'll have this. So in order to measure the SNR here, we'll have this user located at Z as a serving user, and all the users which are outside of this typical cell highlighted by these black lines outside of this typical cell V0. all these points are the interfering points, which are denoted something like by psi tilde. And this exact characterization of psi tilde is very difficult to do. So for that purpose, actually, we'll be relying on some approximation. So the uplink SNR received at this typical base station can be written something like this. So this is the signal power which is received over this desired link indicated by the green color, and divided by the interference received from the all the devices within this interfering point process. And remember, because of this power control fraction, we are having this fraction alpha in the path loss models, in the path loss. So now the distribution of this link distance is again very hard to derive. So we have actually kind of derived this approximate distribution, which is again kind of wide probability with the corrected or modified density. So the density of this C1 times lambda, where C1 is kind of 9 over 7. And the point process of the interfering base stations. So remember, we need for the analysis, we need two metrics. One is a distance distribution of R0, which can give you given something like that, and another quantity that is distribution of this interfering point process. So and it is very difficult to derive because it is kind of inhomogeneous point process. And why it is inhomogeneous? Because no interfering user are supposed to lie within the typical cell, actually V0. So actually we rely on the approximation, and for that purpose actually we first derive the approximate pair correlation function, which is derived something like this. And here you can see that for the smaller value of R, this is kind of this is kind of a very small quantity than 1, and as R increases to 1, as R increases, this quantity is actually asymptotically turns to the converges to the 1, basically. So that means for the smaller r, there is kind of repulsion. I mean, since g of r is, for smaller value of r, g of r is kind of less than 1. That means there is a repulsion between this point and the interfering point process for the smaller values of r. And then using this pair correlation function, we approximate the distribution of this point process psi tilde using non-homogeneous Poisson point process, and its density actually goes something like this. So that means it's just the lambda times gr scale with the lambda. So again, we do the conditional successful probability, just averaging over the fading gains, that is EHX. And then we derive for deriving the bit moment of the conditional successful probability, we actually take expectation with respect to these three quantities. This R0 and R phi tilde is same as, sorry, this has to be psi tilde instead of phi tilde. It is same as that we did for the downlink, but in addition to that, here we have Rx actually, which is coming because of the distance dependent power control. And with by applying this PGFL of this non-homogeneous approximation of this interfering point process, and then link distance of this link distance distribution, we can actually arrive at this triple integral expression actually for this bit moment of the meta distribution. And here I'm just plotting this successful probability, that is just the first moment of this meta distribution, and for various values of the power control fractions. So for power control fraction, when it is 5 or setting higher values of this power control fraction is useful for the lower region of the SINR. However, for higher regime of the SINR, no power control actually is necessary. That is, epsilon should be equals to 0. That will give better result basically. So thank you for attending this presentation, and and you can ask me if you have any doubts.
Yeah, thank you, Praful. Now, there were a few, there was one particular doubt at the beginning of your presentation. So I guess if required, you might have to again share your presentation.
Okay.
Yeah. So the question is, can 2 points be co-located as the distribution is random? Since the distribution is random, can 2 points be co-located?
Actually, the probability of being that is very small. It will be almost equal to 0. But they can be orbitally close to each other. They cannot be co-located actually. Right? Means 2 points can be as close as each other, but they will not be at exactly at same point. In fact, for the Poisson point process, no 2 points are at the equal distance from the origin. That means no 2 points can be co-located. But they can be as close as they can be very close to each other with the infinitely smaller difference between them.
Yes, so that's true. If participants have any more questions, there is one more question here. So, is this interference applicable? I guess what participant means is whether the interference analysis is applicable if the distributions are non-uniform as well.
Yes, this Campbell theorem is kind of generic, though I have presented. Let me look at that. Yes, so this Campbell theorems and then so these two theorem actually will be able to make the interference analysis, at least first and second movement of the interference. And yes, these are kind of general properties for it. It is applicable to any point process, but I have just presented in terms of the Poisson point process. So answering your question, yes, it is possible.
Yes, so if the participants have any more queries, they can please raise them. So I think I will ask you one question, Doctor. Okay, fine. So here we have Vikas Gupta sir, who is asking what kind of simulator did you use in order to obtain your results, that is validate your theoretical concepts?
Yes, actually, we have used MATLAB, and simulating in MATLAB is very simple. It's just that there are only 2 steps to simulate this Poisson point process. One is based on your simulation window, you just take this random Poisson number of random variable, which is just with mean equals to density that you want to set and the area of your simulation window. So once you have this n as a number of points, then you distribute this n number of points uniformly at random over the whole simulation window, and that will be your realization of your Poisson point process. And then you make a note of SNR or interference or whatever the metric you want to, and then do it just note down that one sample and do this spatial realization iteratively multiple times, so that you will have multiple realization or many sample values, and then using that sample values you can plot the distribution. So that will give you the simulation result, and analytical result actually you derive through these properties and these results, and then you try to match with the simulation. Yeah.
Sir, I have one doubt.
Yeah. Please go ahead, sir.
Sir, my name is Banath Ravi.
Hello.
Sir, Praful sir, I have one doubt. Sir, this stochastic model is applicable for network layer in ad hoc networks. How we can consider network layer parameters by using stochastic model? For which quality of service we are going to improve by using this stochastic model?
Yes, actually, the network layer or the higher layer parameters, which will actually amend your transmission strategies. For example, the MAC layer parameter of the Aloha system that you are transmitting at this at particular time instance, right? So
Okay.
we have considered. So, for example, in this setup, we have considered Aloha kind of setup. So,
Okay.
based on your MAC layer actually, or the higher layer constraint, the activities of your transmission activities will go down or up depending on other parameters.
Means you are
Of
saying
like,
mobility.
no, I'm not saying mobility. I'm just saying the
Okay.
activity of the transmitter, means whether it is active or it is transmitting or not transmitting.
Okay.
Okay, and once that kind of that probability is given to you, then you can start to straightforwardly apply this kind of models, and that probably may not be uniform for all of the points,
Yeah.
right? Means
Okay.
certain points, certain base station will have a higher activity, or certain
Yeah.
base station will have lower activity, but still you can actually do the analysis. Maybe not in straightforward way that as we did here, but but you can do that also. Yeah.
Okay. Thank you.
But the real issues come actually when the network layers or these transmission activities of the different transmitter gets coupled with each other, like in the fractional traffic scenario, because of
Yeah.
the service rates of these transmitters are correlated with each other through the interference, right? Means
Yeah.
if one transmitter is transmitting, then it starts to make the interference to its neighboring transmitter and increases service time also. And then it's because of its increased transmission, then he will revert back to the first transmitter, and which will elongate the service rates or the transmission times of this two transmitter together. So this kind of system are actually very difficult to analyze, but people are actually still struggling with the analysis of this to cover the spatiotemporal analysis actually. But
So
yes, to answer to your question, it is still possible as long as we can narrow it down uh, or we can summarize the higher layer parameters in terms of the activity of of the the transmitters.
yeah, exactly.
Yeah,
Yes. Thank you, sir.
yeah.
I think Vikas sir has another question, but you almost, I think you had answered it before. But nevertheless, he's specifically asking whether you have tried any other distributions in addition to the Poisson distribution.
Yes, I have also worked on the let me go back to this one slide. So in particular, I have tried this Thomas cluster Poisson point process. So what happens is kind of doubly Poisson point process. So we realize the cluster. So we realize the clusters of this multiple cluster basically. So to represent the hotspots in the city. So with this density function, we realize a cluster and then shift this cluster to the different locations. Yeah. So that will form the Thomas cluster Poisson point process. Or in general, Cox Poisson point processes are actually kind of covering this clustering effect to capture the hotspot scenarios into the wireless networks. So it's just that we have to, adopt to appropriate density function as per our need.
So, sir, one question is which software can be used to analyze parameters of any distribution? I think it's in the general sense, that is, since you are using MATLAB, whether that can also be used to analyze distributional parameters, or are there any other powerful softwares when it comes to such stochastic parameters?
No, there have not been any software, but there are some mathematical tools that some of them I tried to give here, like this K function and J function. Once you have this real life data, you can apply this kind of functions, right? Means when you have real life data, actually you can evaluate this G of R and F of R precisely, and then know that know that whether j of r is above 1 or below 1 or is equal to 1. If it is 1, actually, then it's a Poisson point process. If it is above 1, then it's a cluster point process. If it is below 1, then it's kind of repulsive point process. So that means by applying this kind of tools, actually, you can get some initial insights into your distribution of your data, your real points.
And sir, let me ask one final question. So while running the simulations, and you would have to do it extensively over several thousands of iterations. So is it possible to do it on a standalone system, or do you need a server or a powerful system in order to get these results that you have shown us?
No, these calculations are very basic. So I think standalone system is kind of enough, provided it has a sufficient RAM and yeah. Yeah, but if you are actually it depends. If you are going for so in this presentation, actually we have talked about very simple setups of the cellular network. But if you are going into kind of bit complicated system model like millimeter wave communication or the UAV communication, or having massive number of IoT devices, like IoT devices wherein the massive connectivities will require, right? So you will have massive number of IoT devices which are uploading their data. So the points in your process will just increase actually. And if you are increasing that, then you'll probably need these servers basically.
Okay, sir. Thank you very much. And I guess there are no more questions as of now, but you can always reach out to Dr. Praful. His details are available on the IIIT Hyderabad website. So I take this opportunity now to thank Dr. Praful for an excellent technical session, which contained in-depth mathematical analysis, and I hope that the participants have got a flavor of the analytical aspects that go into capacity evaluation in the context of cellular networks, and also the fact that these models or these tools, such as stochastic geometry tools, are going to play a huge role in the analysis of future generation networks, including 5G, considering the heterogeneous nature of such networks. So thank you, Dr. Praful, on behalf of all the participants and on behalf of Atal Academy and Goa College of Engineering. I thank you very much, sir, for being there with us today and for this wonderful presentation. Thank you, sir.
Thank you, sir.
Yeah. Thank you. So now, just to inform the participants, we will wind up this session. The next session will be at 3 o'clock, and it will be a video demonstration on test bed setup for 4G and 5G. So please be present at 3 p.m. and the same Meet link will be valid in the afternoon as well. So please use the same link. Thank you very much, and see you at 3 p.m.